Okay, part 3 of chapter 20 of Martini. This is a short segment. It really ought to have more in it than it does, but we're going to focus in on what's essential. And that is that to supply the ATP that cardiac muscle cells need to keep your heart beating day in and day out for the rest of your life requires a continual supply of oxygen. You do have some oxygen storage in myoglobin in your cardiac muscles. Remember, myoglobin from skeletal muscles, it helps make the muscles red. But if you cut off the blood flow to the heart, we already know you're going to have a myocardial infarction. So you need that continual oxygen delivery. Cardiac muscle cells can actually break down other fuel molecules besides just fatty acids and glucose. They're really good at providing enzymes to break down other organic molecules. They can even break down lactic acid from anaerobic exercise, ketones, which can be available in higher concentrations if you're on a high protein diet or a starvation diet or you have diabetes. So it's not just glucose and fatty acids. There are other organics that heart cells can eat, but they absolutely crucially depend on oxygen. All right, so that's just a little tidbit of information. We're going to move on now and talk about the cardiac cycle. The cardiac cycle is at the organ level what happens as the heart goes through one heartbeat. So from one heartbeat to the next is a single cardiac cycle. We have to have two phases. The heart is a pump. It has to fill before it can empty, and then after it empties, it has to fill again. So our two phases are systole and diastole. Systole is contraction, and diastole is relaxation. And that's true for the atria and also for the ventricles. I know that this slide says within each chamber, but it's really the atria contract together. So you have atrial systole. They're coordinated with each other. You can't move the right atrium without also moving the left. So you have atrial systole, followed by atrial diastole. As the atria go into diastole, the ventricles begin systole, and then they go into diastole, and then you have a period of complete diastole where the heart is just filling, and then you start back over with atrial systole. Let's take a look. So here's a diagram out of your book of the cardiac cycle. We're going to start at the top with atrial systole. Atria contract. Notice that lasts about 100 milliseconds, and then atrial systole ends, and we're into ventricular systole. Notice the color coding, the purple outer ring, ventricular systole. The green ring on the inside, atrial diastole, notices the entire rest of the cycle. Ventricular systole lasts about, it says 370 milliseconds. I think we can round that off. So we were at 100, so if we round that up to 400, then that means ventricular systole lasts around 300 milliseconds. And then the rest of the cycle, to get us to the 800 milliseconds, so the last half of the cycle, 400 milliseconds, is that period of complete diastole when the chambers are simply filling with blood. So taking a look at the little diagrams of the heart, during atrial systole, notice that the atria are contracting. That's what the little green arrows mean, and the black arrows indicate that blood is flowing from atria to ventricles. And then as we move into ventricular systole, the ventricles go from relax to contract. They close the valves. That's in the upper figure on the right. They close the AV valves, and then the semilunar valves open, and that allows blood actually to get pumped through. So we have two phases to ventricular systole. In the first phase, we've just got the valves completely closed. It's a very short phase, doesn't last very long. And then in the second phase, most of the phase, you're actually ejecting blood from the heart because the semilunar valves are open. And then as ventricular systole ends, the ventricles rather abruptly start to relax, and that lowers the pressure. And as the pressure lowers, very quickly, the semilunar valves are going to close, and once again, we're in a state where all the valves are closed. Again, that's very short. And then as you move to the figure at the upper left, ventricular diastole, the second phase, notice that blood is filling in from the atria all the way into the ventricles. It's not it's not just sitting in the atria like it is in the lower figure. It's getting all the way to the ventricles. Now, they don't show those black arrows with blood coming in on to the atria on the right side, but they should. Your atria are collecting blood the whole time they're in diastole. All right, so going through that again, we're in the first part, atrial systole. You need to know it lasts about 100 milliseconds. You need to know that during this period, blood is flowing from the atria through the AV valves and into the ventricles. As we move into the first part of ventricular systole, the first thing that happens is closure of the valves. Now, all the valves are closed. There's not any blood coming in or leaving. And then the late phase of ventricular systole, the blood's actually ejected from the ventricles to the pulmonary trunk and the aorta. And as that ventricular pressure exceeds it and the semilunar valves open and blood is ejected, it's going to push the blood out for close to 300 milliseconds, 250 to 300 milliseconds. Then we get into diastole. Again, notice that all the valves are closed. Notice that blood is coming into the atria, and it's just sort of sitting in the atria because it can't go anywhere yet. But as the ventricles continue to relax, the pressure in the ventricles continues to drop, the blood is still coming into the atria, and the pressure becomes high enough to push open the AV valves. Okay, so we have this nice, let's see if this is going to work. It's not. Let's see if I can get this to work. It's a nice smart art video, and I'm hoping the sound is going to work.
Cardiac cycle. Diagram here is a single cardiac cycle, which lasts about 800 milliseconds, or 0.8 of a second. Let's begin here at the red arrow labeled start. In this first image of the heart, all 4 heart chambers are relaxed, therefore in diastole, and partially filled with blood. Atrial systole, also known as contraction, begins and completes ventricular filling. Notice, the green arrows show the atria contract, and the black arrows indicate blood flowing into the ventricles. Atrial diastole follows and continues until the next cardiac cycle begins. Ventricular systole now begins, and is a process divided into 2 phases. The first phase, shown in this figure, is isovolumetric contraction. It is called isovolumetric because the volume of blood within the ventricles does not change. During this initial phase, ventricular contraction closes the atrioventricular, or AV valves. The second phase is ventricular ejection, when the ventricular pressure finally exceeds the pressure in the arteries, and that pressure increase opens both the aortic and pulmonary semilunar valves. Blood now exits the ventricles and is forced into the aorta and pulmonary trunk. Here, in early ventricular diastole, blood flows backward towards the ventricles as ventricular pressure rapidly drops. This backflow of blood against the semilunar valves causes them to close. At this time, blood is also flowing into the relaxed atria. Notice here, the AV valves are still closed. This phase is called isovolumetric relaxation. Finally, in late ventricular diastole, all chambers are relaxed and filling passively to about 70% of their capacity. To summarize, a single cardiac cycle includes atrial systole, when both atria contract at the same time to complete ventricular filling, followed by ventricular systole. Isovolumetric contraction is the first phase of ventricular systole and causes the AV valves to close, while the second phase is ventricular ejection, which opens the semilunar valves as blood is forced into the arteries. As blood pressure rapidly drops in ventricular diastole, the semilunar valves close and the ventricles begin to fill again as all 4 chambers of the heart rest and passively fill prior to the next cardiac cycle. So what? Why is it important to understand the events of a normal cardiac cycle? Well, this is crucial to understanding many serious heart conditions. For example, suppose a patient has a myocardial infarction, also known as a heart attack, that has seriously weakened the left ventricle. Left ventricular ejection will decrease, blood flow will back up between the left and right sides of the heart, resulting in congestion in the lungs. The resulting respiratory complications can be life-threatening. And to understand the many congenital defects of the heart, it's important to grasp a normal cardiac cycle, as these cardiac abnormalities interfere with normal blood flow and valve function.
Remember, you can always rewind and watch that again if you think you need to. So we're going to be trying to graphically represent what's happening during a cardiac cycle. So we're going to pay attention to blood pressure. If the blood pressure, if the chamber of the heart is in systole, then the blood pressure tends to rise until the blood is actually emptying and leaving the heart. And then when the heart is relaxing, then the pressure is going to fall. Remember that blood flows from high pressure to low pressure, so the pressure of each chamber and the pressure in the arteries is crucial to understanding the normal blood flow. And to keep the blood from flowing backwards, we're going to have those one-way valves, the AV valves and semilunar valves. All right, the cardiac cycle at a normal heart rate of 75 beats per minute lasts about 800 milliseconds. That's 0.8 of a second. If you speed up the heart, you have to speed up all phases of the cardiac cycle. You can't just shorten the period of diastole because that would just cut off the filling period. So everything speeds up when the heart is told to speed up. All right, so we have our phases: atrial, systole and diastole, ventricular systole and diastole. You need to be able to recognize them. You need to know the timings of each one. And you need to know the events that's happening during systole and during diastole. So if the atria and diastole, they're filling with blood. Now, there's some points here that we have to pay particular attention to. When the ventricles get to the end of diastole, they're holding as much blood as they can. So the end diastolic volume is the fullest the ventricles are going to get. And then when they contract, the first thing that happens is that those AV valves close, and that gives you a period of isovolumetric contraction. Iso means equal. Isovolumetric means the volume doesn't change. That is, no more blood's coming in, but no blood is leaving either. So then once the semilunar valves open, then the ventricles can actually eject the blood into the pulmonary trunk and into the aorta. The amount of blood ejected in one beat of the heart is called the stroke volume. A beat of the heart is called a stroke. So stroke volume is the amount of blood ejected in one beat of the heart. And then as the ventricles go into diastole and the pressure starts to fall, the semilunar valves will close. Now they're as empty as they're going to be. So at the end of systole, the end systolic volume is about as low as it's going to get. And the percentage is going to vary, but your book says 40%. So somewhere around half the blood has been ejected in one beat of the heart. All right, so here's our graph. Now, what I want you to do when you look at the graph, the first thing you have to do is you have to look at the lines. Let's figure out what the lines are, and then we'll correlate them with the labels at the top. So you see a black line toward the top labeled aorta. You see a red line. That's the left ventricle. The right ventricle is going to do something similar. It's just going to be at much lower pressure. And then a blue line, that is the left atrium. Notice the atrial pressures are always low, somewhere around, practically 0 to maybe 10 or 15 millimeters per mercury is our units. The aortic pressure is always high. It goes from 80 to 120, which you probably remember is the normal range for blood pressure in systemic arteries. Now, look at what the red ventricle line does. It goes from lower than the atrium to higher, or about the same, as the aorta. So the ventricular pressure at its lowest, down there at 1 and 2 and almost to 3, is the pressure in the ventricle has to be lower than the atrial pressure so that blood will flow from atrium to ventricle. But then, notice at point 3, the pressure lines cross. As the ventricular pressure gets higher than the atrial pressure, the AV valves close. And then the chamber's completely closed, but it's still contracting. Notice how the pressure in the left ventricle just shoots up from about 15 to about 80, and as it crosses the aortic line, what that means is the ventricular pressure is higher than the aortic pressure, and that pushes the the aortic semilunar valve open. And when that opens, then blood starts to leave, but the ventricle is still contracting. So up to about 0.5, you have the ventricle continuing to contract, blood continuing to leave out the aorta, and of course the same thing's happening on the right side. And then at about the peak of that pressure curve, at about 5, the ventricle quits contracting any smaller than it is. It's just kind of sitting there in a contracted state. And since the blood is continuing to leave out the aorta, the pressure starts to fall. And so that pressure line is going to start to drop, and we'll see what happens in another slide. So during ventricular systole, the pressure line in the aorta climbs from about 15 to about 120 in a time span of about 100 milliseconds. So get your bearings at the top with ventricular and atrial systole and diastole. And then let's look at the bottom figure. This bottom figure is showing us the volume of blood. Remember that the end diastolic volume is the highest. So as the AV valves close, they're at 0.3. No more blood's coming into the ventricle. So these are resting values. So the high is about 130 milliliters. Notice at 0.2, that's when the atria are contracting. So you get a little surge in pressure or in volume in the left ventricle because the blood is getting squeezed in from the atrium. We're working backwards here, so up to 0.0 on our graph, blood is just passively filling into the ventricles. At 0.2, the atria are ejecting about, maybe 20 milliliters more, 20 or 30 milliliters more blood into the ventricle. And then at 0.3, those valves shut and no more blood comes in. And then once the aortic semilunar valve opens and blood can leave the ventricle, that volume line starts to drop. So isovolumetric means that the valves are completely closed. If we're in diastole, that means the heart's relaxing. So as the ventricles start to relax, the valves close, and then the AV valves are going to open and allow the ventricles to fill passively. And we're going to see that on the graph here. Here's the rest of our graph. So starting at the very top, where we're at 120, we see our ventricular pressure line, that's the red line, dropping very rapidly, but as soon as the red line crosses the black line, that's the aortic line, the aortic valve closes, you get what we call the dicrotic notch. You notice there's a little bump there. That's because of the pressure surge when the semilunar valves close. And then the pressure in the aorta just gradually declines to about 80 again until the next heartbeat. But in the meantime, the ventricular pressure line is dropping like a rock. It drops below the blue line, and where the red line crosses the blue line, that's where the AV valve is going to open back up. Notice the blue line's been gradually increasing up to that point because the atria are filling slowly with blood. But now that the AV valves are open, blood can flow straight through from atrium to ventricle. So we're in period 8 where the AV valves are open and we have passive ventricular filling. And you can see in the lower diagram, the lowest volume occurs about the time the aortic valve closes. That's our end systolic volume. And it dropped from 130 to about 50. But then notice, line up when the AV valve opens. And now the volume curve starts to go up, and it goes up gradually from about 50 to about 90 or so, 90 or 100. And then the atria are going to contract again and give us that last little surge there at the end. Okay, the heart sounds. We're only going to worry about the first two, sound 1 and sound 2. Sound 1 is the closure of the AV valve. Sound 2 is the closure of the semilunar valves. Yes, you can hear abnormal heart sounds. They're very often called murmurs. If the valve isn't closing right, if there's scar tissue on the valve, or if the valve has been dilated somehow, or damaged from rheumatic fever, then you get these gurgly sounds called heart murmurs. Most of the time, they're not going to provide any symptoms, and so you're just going to live with it. But if it gets bad enough that it affects your circulation, you may actually have to have a valve replacement. All right, so this is beyond, we're not doing this much diagnosis. If you know that the first heart sound is the closure of the AVs and the second heart sound is the closure of the semilunars, I think you're in pretty good shape. All right, so now here is the complete graph. And what I want you to do here is line up S1 and S2. So you see S1, the jiggly lines of that heart sound, start right after the AV valve closes, and S2 starts right after the semilunar valves close. And the other sounds we're just not even going to worry about. Okay, so now we're going to move on and talk about cardiac output, and as we do that, we'll get into regulation of the heart as well. So I'm going to stop it here. We've been going for about 20 minutes, and I'll continue this in the next part.